Hello and welcome to the second Physics 2211 lab, Motion of a Falling Object. The purpose of this lab is both to compare the effects of drag on a falling object and to create a model to predict the motion of a falling object. As background information, we know that acceleration due to gravity, or g, is negative 9.8 meters per second squared. We also know that the gravitational force given by F sub g is mass times g times the j unit vector in the negative direction. We also know that the drag force given by F sub d is the drag constant times speed squared times the direction of the velocity times -1. As a preview, we know that the model that included the drag force was more accurate than the one without it, since there is actually a drag force acting on the falling object. In this lab, we assume that the only forces acting on the falling object are gravity and drag. We also assume that the object is falling in a 2D plane rather than in a 3D plane, since it would, in reality, be difficult to model this experiment in a 3D plane with tracker. The models are the equations for weight and drag mentioned earlier, given by F sub g and F sub d. At this point, we will look at our experiment in tracker. This is a gum wrapper, which encountered a lot of drag force as it was falling, and we determined the point masses as it fell. The initial conditions given in our gravity-only model are the system, which we defined as the falling object or the gum wrapper, and the surroundings, which was a gravity-inducing object or the Earth. And this is reflected in our code where we entered in the initial mass of a gum wrapper plus the initial position of the wrapper, which was given by tracker, as was delta t. In our gravity-only model, our code looks something like this, where the net force was equal to the gravitational force. As we updated the wrapper's velocity and position, we eventually plotted it and found that it was less accurate than the gravity and drag model, which we will look at here. The gravity and drag code also includes an additional parameter, F sub d, and the net force accounted for this by also adding the drag force onto the gravitational force. So then when we updated the velocity and the position, we got a better model for what was actually happening as we dropped the gum wrapper. In our data, we plotted the updated positions in each time step of just the gravity model in this column, the gravity and drag model in this column, and the actual gravity and drag model, which we found from tracker. And as we can see from this chart here, the gravity and drag model was very close to the actual model, whereas the gravity only model was very far off after a certain point. Okay, so now we will look at the what does it mean. At the point of terminal velocity, the net force acting on the system is 0 newtons. At this point, the drag force and the gravitational force are exactly equal in magnitude, but opposite in direction. And we know from vector addition that this means that their sum is 0. And so the gravity and drag model predicts terminal velocity because it shows two separate forces which eventually become equal to each other. This is when we reach terminal velocity. And the terminal velocity is approximately negative 0.375 meters per second. Okay, now let's look at the what if. Here, in this instance, we dropped the gum wrapper from a velocity of 0 meters per second. In this instance, we dropped the gum wrapper with a velocity of negative 0.5 meters per second. And we find that in both instances, the terminal velocity is exactly the same regardless of the initial velocity of the object. So in conclusion, we see that the gravity and drag model was far better at modeling the falling object than the model with just gravity. This suggests that there is both a gravitational and a drag force acting on the falling object. And we also learned that terminal velocity is not dependent on initial velocity. Thank you.